Isaac Newton is famous for creating an equation relating the stress exerted on a fluid to the gradient of the speed of its flow. Newton's law of viscosity equation is as follows. Tau yx is equal to eta times du dy, where tau yx is the shear stress exerted on the fluid, eta is the viscosity of the fluid, and du dy is the velocity gradient, or the shear rate. However, this equation only applies to what is known as Newtonian fluids. Newtonian fluids have a constant viscosity, and so a graph of the velocity gradient versus the shear stress will be linear. Newtonian fluids are ones like water and air. However, many fluids that we come across in our day-to-day lives are non-Newtonian. Their viscosity changes when the velocity gradient changes. Remember the classic cornstarch and water experiment from grade school? That mixture is a non-Newtonian fluid. Here's a quick clip displaying its behavior in slow motion. In a Newtonian fluid, if you double the speed at which a fluid is flowing, the resistant force, its shear stress, will also double. This is not the case for non-Newtonian fluids. Non-Newtonian fluids have unpredictable reactions to force. For some fluids, doubling the speed will more than double its stress. These fluids are called dilatant or shear thickening fluids. A graph of the velocity gradient versus shear stress will curve upwards, similar to a positive parabolic curve. On a molecular level, particles in dilatant fluids act differently under stress than under no stress. When there is no stress acting on the fluid, particles' repulsive forces allow them to flow past each other, causing the fluid to flow as if it were Newtonian. But when a stress is applied, the extremely small interparticle forces are not enough to repel the particles, so they clump together. These incompressible clumps are called hydroclusters. Particles have a harder time flowing around hydroclusters, which is what increases the viscosity of the liquid. The particles act more like solids when force is applied. An interesting example of a use for shear thickening fluids is liquid armor, which is Kevlar soaked in a solution of silica and one of polyethylene glycol. This allows the armor's viscosity to dramatically increase when hit. This phenomena is the same reason why you can walk on a cornstarch solution and not break the surface, but as soon as you stop walking, you sink into the mixture. High shearing stress changes the viscosity of the fluid.
Non-Newtonian fluids can also act the opposite way, where doubling the fluid speed will less than double its stress. These fluids are called pseudoplastic, or shear thinning fluids. Common examples of these are ketchup and whipped cream. This helps explain the great ketchup mystery, where at first it is almost impossible to squeeze ketchup out of a bottle, but after shaking it hard enough, it comes out all at once. Boo-hoo. Once the ketchup bottle is squeezed, pressure is released and causes the particles to gain velocity as they exit the can. This allows the particles to move more like a liquid versus a stagnant solid. The last kind of non-Newtonian fluid, the Bingham fluid, acts surprisingly similar to Newtonian fluids. At and above a certain force, Bingham fluids will behave exactly the same as Newtonian fluids. That is, the shear stress will act linearly with fluid velocity. The force that it takes for this to happen is called the yield stress. This means that on a graph, the line will start at a y-intercept that is equal to the yield stress, instead of the y-intercept of 0 that Newtonian fluids have. Some good examples are toothpaste and mayonnaise. On the molecular level, Bingham fluids often contain particles or polymers whose interactions create a weakly held solid structure. A certain amount of force, the yield stress, is required to break this structure, which allows the particles to flow as a liquid under viscous forces, but once the force is removed, the solid structure reforms. That is all the knowledge we have for you on Newtonian fluids today. Thank you for watching.
Thanks for watching. Stay viscous, chemies.